A logical scalar is an expression in MATLAB that produces an output in the form of a one-by-one logical array. The assigned value of a logical scalar takes on one of two possible values, either logical 1, which stores the idea of true, or the other option would be logical 0, which stores the idea of false. When we evaluate a logical scalar, or the expression that puts out a logical output, MATLAB assigns the scalar valued output, the one-by-one output, based on the truth value of the corresponding expression. The reason that we use the term logical scalar is we're going to distinguish between things known as logical scalars, logical vectors, and logical matrices. Logical scalars are variables stored using the logical data class whose dimension are exactly one by one. The concept of a logical scalar in MATLAB is very much related to another idea in broader mathematics known as a proposition. We say that a proposition is a mathematical statement that has exactly one truth value. Either a proposition can be true, in which its truth value is capital T, or a proposition can be false, in which case we assign a truth value of capital F. Notice that a logical scalar is a MATLAB data class that allows us to encode in MATLAB the corresponding concept of a truth value for a mathematical proposition. Let's take a look at an example of how we might do this in mathematics. Suppose we call this mathematical statement 2 to the 4th equals 8. Let's call that proposition P. So proposition P has a truth value. It is a mathematical statement written in mathematical symbols. In this case, we're claiming 2 to the 4 equals 8. Remember that every proposition has an assigned truth value. It is either true or false. Under the rules of standard algebra, 2 to the 4th is not equal to 8. Specifically, 2 to the 4th represents base 2 multiplied by itself 4 times. Well, 2 times 2 times 2 times 2 is 16. 16 is not equal to 8 in the natural numbers, so proposition P, 2 to the 4th equals 8, is actually a false proposition. This does not have a truth value of T or true. On the other hand, if we look at proposition Q, 2 to the 4th equals 16, that is a mathematical statement, and indeed that statement holds. The expression on the left-hand side, when evaluated numerically, is equivalent to the expression on the right-hand side. In other words, the truth value of proposition Q is true. This discussion really focused on a logical analysis of different mathematical statements. The concept of a logical scalar allows us to encode that mathematical analysis using a construct within MATLAB's memory. Let's go ahead and see what we're talking about here. Each of these propositions is actually what we call a relational operation. I'm trying to relate 2 to the 4th to the number 8. So in this situation, let's go ahead and do this in MATLAB. So if I take 2 to the 4th, let's ask ourselves, is 2 to the 4th the same thing as 8? MATLAB returns the logical scalar 0. The reason this is a logical scalar is that it is a one-by-one array stored using the logical data class. And MATLAB is telling me the statement 2 to the 4 equals 8 is a false statement. In other words, this produces the value of 0. I could actually store that. So if I set test, the variable, equal to the output of the relational operation 2 to the 4th equal 8, notice MATLAB is telling me this test came back false. The statement in this relational operation is a false statement. On the other hand, let's go ahead and test a second time. Let's test to see if 2 to the 4th is equal to 16. This relational operation, MATLAB is telling me the second test that you run produces a value of 1. In other words, this relational operation is evaluated as true. Notice the results of each operation are stored as logical scalars. In other words, this expression is a logical scalar. It outputs a logical value in a one-by-one array that indicates the truth value of the corresponding proposition that I've typed up in the command window. This concept of logical scalars and logical variables has a very rich history in computer science. In fact, I would claim that the entirety of computation depends on the idea that we can implement logic rules in mathematics using electronic signals in digital electronics. In fact, almost every single electronic computation machine on Earth today maps back to a very simple idea. that we can implement the concept of a truth value. In other words, we can use true and false ideas to map to logic values, which are stored as either ones or zeros. And then we can use actual voltage values on electronic components to make a connection between logical 1, which in this particular idea is stored as a high voltage, and logical 0, which is stored in a low voltage. Depending on the type of computer hardware that we have, each hardware company will determine its own high and low voltages to use when designing a computer. So for example, there are computer architectures designed by the company TI, Texas Instruments, where the high voltage will be something like 3.3 volts and the low voltage will be something like 0.5 volts. In other words, logical values of 1 in the computer, if we were to actually go down to the hardware level and measure a voltage using a voltmeter, that would be stored at 3.3 volts. On the other side, if I saw a logical value of 0, on the actual hardware in the computer, that might be stored in a voltage value of 0.5 volts. The concept of digital computation is to map voltage levels to true and false statements in mathematics. The moment that we have this connection between hardware and a computer, logical values in software, and true and false values in mathematical analysis, we can do almost any mathematical operations, not only via pencil and paper, but map them back into the manipulation of electronic signals within a physical circuit. That is the major concept behind digital electronics, and we will see that show up over and over and over again in this course. The point of logical variables is to actually capture this using a data class so that we can write code to take advantage of true and false statements and build sophisticated computational algorithms from this very simple idea. MATLAB's logical data class is designed to allow us to store, capture, and manipulate that type of true and false data using MATLAB variables. Anytime we see a variable that is stored using a logical data class and whose size is 1 by 1, we immediately know that is a logical scalar. It's stored using the logical data class and it has size 1 by 1. Variables stored using the logical data class that have dimensions or sizes that are larger than 1 by 1 are not logical scalars. Those might be logical vectors or logical matrices. That's the exact topic that we're going to talk about in our next video. Of course, you're always welcome to post your comments and questions in the comment section below. Thank you so much for your attention, and I'll see you in the next one.